Hello, we have a set of problems today. We're gonna do them. Maybe there are one, two, three, four, five, six problems. So the topic is the electric field of finite charge distributions. So these are this wire on which the electric charges reside. It's a finite size wire. If it's an infinitely long wire, we have a better way of doing things. Similarly, this is on a finite. Here is a square. It's basically application of the formula you'll obtain from here to here, and then there is a ring on which they have a finite size ring, and then you have a finite size disk, a spherical shell, and solid sphere. It turns out when you have systems like this, and that, and the disk, you really have to do the integral. Okay, so there's a only recourse, very fundamental definition, and we'll talk about that. So the fundamental formula that you will need is if I have a charge Q here, and this is where I want electric field, that's the point P, then the electric field by this charge at that point, if this is a plus charge, then it's pointed in that direction, and so direction is in that direction. And if the distance is r, then you can write E at P in a vector form is going to be k, whatever the charge is, and then this r square u hat. So we'll just apply this to these cases, and it will turn out to be integrals. You can do all of this with this in doing the integrals. However, when you have a symmetry such as over here, we will apply what is called Gauss's law, and you will see in Gauss's law a lot of simplification takes place. You use a lot of symmetry arguments to build expectation in what you will find here. What the electric field will be here, you build the expectation based on symmetry. Okay, and then the calculation becomes really simple and almost trivial. Okay, but that's for another day. Okay, so let's get going with these guys, and let's see how things will work out. I'm going to erase these guys just to get a space and do these three carefully. Okay, so over here, we will just write down a general integral, and then for a general point. So let's see, for point P, we want to write down, and let's call this an xy plane. Okay, at some arbitrary point. And let's also endow this with a coordinate system that goes like this. X is this way, maybe the y is P3 is on the y-axis, y is that way, and the charges are between x equal to 0 minus L over 2, 0, and this is 0, L over 2, 0, right? Okay, let's erase this to have less clutter, and we're gonna do a small amount of charge. Let's call it dq. I want to write this formula for the electric field produced by this. So it's going to be produced depending on the distance, this distance, and the unit vector will be that way. So if you write this this as a vector, let's call this vector r. If you write this as a vector, it's going to be x minus let's see, this is at some y0 y prime 0. So this guy is at that, let's call it prime coordinate, not derivative, it's a prime coordinate, just a label. So r will be x minus 0, x minus 0 I hat, y minus y prime, j hat, and for k hat is 0, right? So those are I hat, j hat, I hat is in that direction, j hat is in that direction, right? These are unit vectors. So this is we want a unit vector in that direction, so we can take this, divide by its magnitude. So this is going to be x I hat plus y minus y prime j hat. X and y are fixed. I want this with that point. So square root of x square plus y minus y prime square. Now all of this will give me using this some dE vector. So this kind of abstract way of writing the electric field from this, we'll call it dE at P by this guy. We just call it this. That will be equal to the charge, amount of charge. How much is it's if I'm calling y prime, this I'm gonna call it dy prime. So we're gonna prime coordinates to locate the charges. Okay, so it's going to become lambda dy prime. That's the amount of charge we have, and y prime goes from minus L over 2 to L over 2. That's where the charges are. Okay, so that's when I integrate over that this stuff, I'll include all the charges. So that is, and we need a k over there, and r square is this x square plus y minus y prime square. That's r square, and then u hat is just this guy x I hat plus y prime y minus y prime j hat over a square root of x square plus y minus y prime square. So now you can see that this is just to get the electric field, all I have to do is integrate this. E of P is just integral over this whole thing. An integral variable is dy prime, so minus L over 2 to L over 2. And you know, it's a matter of looking at what you have and just brute force doing the integral. I'm not going to do the integral, but I'm just going to say that this is how you get it. Now this integral for different points P is going to come out differently. So at P1, E at P1, and this P1 is at P1 x is P1x is D and y is 0. So if I go over here, so this just minus L over 2 k lambda dy prime, and downstairs it becomes x square plus y prime square, and these are the same, so this whole thing 3/2, and this vector just becomes x I hat minus y prime j hat, because y is 0 at this point. So this is x equal to d, y equal to 0, and you can see the y prime integral will be now 0. So this was easy to do. Minus L over 2 k lambda and x I hat and you have a dy prime over x square plus y prime square 3/2. So you can do this integral. Now if you want to do P2 will be x equals to d I hat d and y equals to d, y equals to L over 2, y equals to L over 2. So it's x equal to d, y equals to L over 2. This distance is L over 2. So in this I'll just have to put those values in there. This x, I forgot to do x equal to d here, right? That was a d. X equal to d, and then you include that there, and then you do set up the integral and do the integral. For P3, similarly, I put x equal to 0 and y equals to L over 2 plus d. And then over here, you can see this integral will be just as a completion of this work. You can see that you have a k lambda, x is 0, nothing over here, right? So 0, so you have a dy prime, and so in here y is L over 2 plus d minus y prime j hat, and downstairs you have x is 0, so L over 2 plus d minus y prime 3/2, and minus L over 2 to L over 2, because y prime goes over that, over the source. So you can do this integral. Okay, let's recap what happened, and it's the same things can happen again and again, right? So we use a coordinate system, coordinate naming for the field point or test point, okay? And then we use maybe it's good to use a prime and like a dy prime for the source charges. So where the source charges are, and that sets up exactly what we're gonna be the domain of this variable, or you know, this variable y prime has to be distinguished from this y, because this is fixed while we are collecting contributions of the electric field for each one of these charges at that point. So each one of the charges here is producing its electric field at that point, and I need to add them up vectorially. And adding up the vectorially is what is causing all kinds of problems, right? Because I can't really avoid u hat integral dependent on which charge I'm looking at, right? So like if you have a charge from here, so let's see if the charge was this dq, is u hat from is pointed that way, the other one was pointed this way, now it's pointed that way. So each one has a different, from here it's pointed that way. So u hat points in different direction depending on which part of the distribution you're looking at, and that's what makes the problem. Okay, let me kind of tell you how this will go. This will use one of so like if you look at this, so you will have integral over this to figure out which way the electric field is from this is going to be pointed from the middle down here. Net electric field pointed in that direction, and once you work it out like this way, like as if this was a charge, just like this is a three-dimensional situation for that. And so I'm not going to do this. You're going to find from, say, this is 1, and this is 2, this is 3, this is 4, so you get E1. work that one out. Use E2 will be the same way except from this direction, right? So this will be the E2 will be in that direction, and E3 will be another direction, and then you add these. So the E at P will be E1 plus E2 plus E3 plus E4. So that's the way this will work out. And now I'm going to work this one out, okay, in more detail. Okay, so here is a very interesting situation, and this is a you can say if I have a coordinate system in which we have like this is x-axis and this is the y-axis and this is the z-axis, and point P is at the z-axis. So if you you can exploit the symmetry in the calculation, unless I would let you do that, and there's a lot of textbooks do that, and let's do it the way we are doing it right now without even thinking about symmetry. So this is like a, if you locate the charge on the ring, so this is say dq, you will need this angle, let's call this theta prime, and you will it's in xy plane, so this guy's coordinate will be r cosine theta prime. R is the radius of the ring, r sine theta prime, and is in the xy plane, so this is 0, right? So that's its coordinate. And in order for me to include all the charges, theta prime will go from 0 to 2 pi, okay? And 2 pi is same as 0, right? And this guy's coordinate is 0, 0, z. Okay, so dq is lambda times the what is the size of that, that r times d theta prime using the arc length. Okay, so that's a dq. So if you look at the distance from here, we want to be able to write the distance between the, from the source to the field. So this vector is r. So r vector is just a 0 minus this, 0 minus this, z minus that. So I have a 0 minus r cosine theta prime I hat plus 0 minus r sine theta prime j hat plus z k hat, right? We got all of that. So unit vector will be in that direction. So unit vector is going to be, just take this divide by its length, right? So minus r cosine theta prime minus r sine theta prime plus z k hat divided by its length, and z is actually equal to d. So z is d. So this is just a r square plus d square. That's you can see r square cosine square theta, r square sin square theta becomes r square, or you can just look at the triangle here and you can get this is the hypotenuse. So this is the u hat, and so dE, I'm gonna write how much electric field this guy is producing as a vector at point P. So just a labeling, just so this would just be dq. Dq is this lambda k time lambda r d theta prime, and then we have r square, which is r square plus d square, not even function of theta prime, right? This is a, and then got a u hat. A u hat is a minus r cosine theta prime minus r sine theta prime plus d k hat divided by r square plus this has to be square root of this, square root of that. Okay, so you can now this is the range at which I need to integrate it. So EP, you can see this is the only place theta prime is, and when you integrate, this will give me 0 and this will give me 0. So you can see d theta prime cosine theta prime 0 to 2 pi is actually 0. If we do sine theta prime, d theta prime 0 to 2 pi is also 0, and when you do this you'll get 2 pi. So this will be k lambda r 2 pi d k hat over r square plus d square 3/2. Of course you could write this, this will be the total charge that's on here on the ring, right? So 2 pi r is the radius and lambda is the charge per unit length. So this is so this is the answer for this. Okay, let's do the disk. See how what the disk will turn out, and I'm going to set it up, and we're picking a very arbitrary point on the z-axis, right? Now when you try to do this thing for an arbitrary point over here, say p2, it's going to be hard. This integral will be hard and not going to be so easy to do. Okay. All right, you may want to do it, but that's usually you don't do it because messiness of the integral. So this is charge is distributed, and this is sigma, this coulomb per meter square. And again, on the symmetry axis, we are looking kind of like that. Point is P, this distance is D, and radius is R, capital R. So the way we're going to do this is use this answer, okay, for a ring, of size. So if I had a ring of radius little r, okay, and thickness r prime, little r prime, dr prime, we're dealing with the source, so just put a prime on there, just make sure that we're dealing with force. And so this is still 0 d, this is z-axis, so it's kind of like that for this ring. So all the charges in this ring, if you look at how much charge is in that ring, is what's the area of that, is going to be 2 pi r prime dr prime, and times sigma, this will be the dq, the charge on the ring. So when we work it out, that's the total charge, this is the charge on the ring, so that will change that. And so using this, we'll have a dE from this ring. So this is a ring problem, so just gonna be translated properly. Capital R will become the size of this little ring, so dEP will just be K. How much charge in the ring? That's a 2 pi r prime dr prime sigma. That's how much charge in the ring. The distance is d, and it's a k hat. This k is different than this k. This k is the 9. K is not related to k hat. Okay, this k is k this case 1.4 pi epsilon naught, or approximately 9 times 10 to the power 9 SI units. Okay, so we got the numerator done. Denominator is going to be little r prime square plus d square 3/2. Okay, very nice. And so integration here, this r prime is 0, r prime less than capital R. That captures all the charges, right? So to integrate, to get the whole thing, we are going to go from 0 to capital R of this variable. And you can see the variable is just sitting here, and it's not so difficult to do. So let's say 2 pi k sigma d. So 2 pi k sigma times d, all this come out, and k hat comes out, and have a 0 to r, and r prime dr prime r prime square plus d square 3/2. Now there's a trick here. You can say r prime square equals to, so x equal to that, so then that makes a dx equals to 2r prime dr prime. And this whole thing, let me erase. So you can see using this, this in here can be turned into 2 pi k sigma d k hat, and half dx, and in the x is going to be 0 to r square, and it's going to be x plus d square 3/2. Further, you can say, well, let's make it, why not change the whole thing? Y equals to x plus d square. That means dy equals to dx, because this d distance is constant. So this turns into even simpler integral, 2 pi k sigma d k hat, and it goes from d square to r square plus d square. This 2 cancels out from that half, and you have a dy over y to the power 3/2. And this integral is very easy to do. I'll recommend you just do it out. So this is using this formula that we obtained for a ring, for this infinitesimal ring on a disk. And this is a very common strategy to build a larger structure using a smaller structure. Okay, you can do the same thing for a shell, a spherical shell, and then from the spherical shell you can build a sphere. We are not going to do that. We're going to instead do electric field calculations in a very symmetric situations, okay, exploiting the symmetry and Gauss's law. That's where we headed next. So we will talk to you later about the next one is Gauss's law. So we're going to talk Gauss's law next. Don't forget to subscribe, and if you like this kind of video, you should hit the like button, because it helps distribute the content a little bit more. I'll talk to you later. Bye.